is to graph the inverse of a function and then describe its relationship to the original. We're also going to be talking a little bit about domain and range as an inverse function and how that's related to the domain and range of the original. And then the last thing here, we're going to determine if a function is invertible. What that means, if it's invertible, that means that we are able to take the inverse. No, I'm going to fix that. No, you can take the inverse of anything. If it's invertible, it means that its inverse is also a function. That's what it is. So remember back in chapter 2, we said, well, there's some requirements for something to be a function. Each input can only go to one output. And so if it's invertible, that means when you do get that inverse rule, the inverse rule also meets the definition for a function. All right, so let's take a look at our information for today. So we still have actually the same intro. We've got the school jazz band that's playing at the frozen yogurt shop. We know from yesterday that it's going to cost us $5 to get into the door, and it's 40 cents per ounce if you also want to fill up a frozen yogurt cup. All right, so we're going to start by revisiting the same function that we wrote yesterday that was giving us the amount of dollars that it would cost to attend the event based on the number of ounces of frozen yogurt. Now, notice that the way that this equation is labeled, it's f of z. Well, this is really the same thing as when we used the variable z. So we were using z to represent the amount of dollars. F of z is meant to be the same thing as z. And so let's actually take a moment here on your paper. I just want you to answer parts A and B. So let's take a moment to read those questions. When it's talking about the function, it's referring to this function right here. It's asking us to identify the input and the output. So you only have two choices. So between number of ounces and dollars, which one is the input, which one is the output. And then we're going to use that to label the axes of our graph. And the hint here is that the input always goes on the x-axis, and the output always goes on the y-axis. All right, so we should have said ounces. So ounces would be the input of the function because that is the variable represented by this little piece right here. It's the number that you would plug in for the variable into the equation to evaluate it. So this equation is used to input a certain number of ounces. When we do that, it's going to output, it's going to tell us the total cost in dollars. So let's go ahead and use that to put our labels in here. If you have not already, so our input on the x-axis, this is going to be the number of ounces. And if you can, I would leave a little bit of space so that we could actually also label some numbers on our scale there. So I'm just going to write that a little bit below. And I'm remembering that ounces is Z. That's where the input goes. And then putting the output on the y-axis here, you could put dollars or you could put cost. I'm just going to stick with dollars and how we were thinking about this yesterday. Instead of using Z for dollars, though, I'm going to think of using the function notation. So I'm going to write this as like f of Z. This is a function based on ounces that's going to output the number of dollars. All right, let's look at the next question here, part C. So the yogurt shop actually restricts the number of ounces that you can get to 24 ounces. So here we're going to find what is the minimum amount of money that you would need to bring to attend the event, and then we're going to find what is the maximum amount that you would need to bring. So I'm going to give you another moment here on your own to work through question C. And we could maybe record our answer something like this. The minimum dollar amount, think about the information, the description all the way up at the top. And then knowing that the most you can get is 24 ounces, let's also determine the maximum. Okay, so let's start to think about the minimum. So remember back in the story, it said that it cost us $5 to get in the door, You don't have to buy frozen yogurt, so you don't actually have to fill up a yogurt cup and pay the 40 cents per ounce. And so if we didn't get any yogurt at all, essentially 0 ounces of yogurt, we would still need to bring $5 just so that we can get into the door. And I'm going to make a little note here that that would be the scenario when the number of ounces is equal to 0. Now let's think about our maximum value. So this would be if we really filled up that yogurt cup. I took my kids to one of these places recently and they went crazy with the toppings. They were putting in gummy frogs that I didn't even know was a thing, gummy bears, sprinkles, berries, chocolate chips. And you would not believe how expensive it was. Maybe you can believe when they put it on the weigh scale, it was like, okay, we're not coming back. But I think they might be closer to this like high end of the weight. And so if we just think about inputting the number of ounces right here, if we do the 24 ounces times 40 cents and then add the $5 onto the end, we end up getting a maximum cost of $14.60. So it must have been $9.60 for just the yogurt, kind of expensive for an ice cream bowl, and then the $5 to get in the door. All right, so now let's take a look at part D. So now we're going to graph the function. We'll talk about the domain and range part in just a moment once we have figured out our graph. So there's a couple of ways that we could think about getting this. I would actually recommend that we start by doing some labeling here on the ounces axis. And I'm just going to label, like counting up by 5, but I'm going to go ahead and have each like little line here, just each square is going to represent 1 unit, but we don't necessarily have to label them all, especially if it's kind of small space and it's hard to fit all of those numbers in. This still gives us some checkpoints. And then we could actually do, I'm going to do the same thing for dollars, of just having each square represent $1. And we could start to think about, okay, well, if it was 0 ounces at the starting point on our graph, how much money is it going to cost us? Well, that was actually our minimum value that we just talked about. It's still going to cost us $5 to get in the door. And so we have this first order point of basically 0, 5. For 0 ounces, it costs us $5. What we could do then is we could look at the next few like checkpoints of ounces, so we could go up to like, okay, what's the cost if it was 5 ounces? Well, 5 ounces times 40 cents works out to be an even $2, which is kind of nice for making our graph. That $2 plus the $5 to get into the door is going to get us up to $7. So if we look at counting on the y-axis here, if each unit, or if each square is 1 unit, this would be $6, this would be $7, and that gives us another ordered pair on the graph. So we could think about just sort of like plugging in these different values of ounces to get the dollars. Another interesting thing that's going on here, another thing we can do is if we actually just look back at the equation right here. We could connect this back to the slope-intercept form. We could actually think about the slope and the y-intercept to think about getting points here on the graph. So this is another kind of review of some things that we did back in Chapter 2. So for a moment here, I'm just going to think about this as like an x and y equation. So it would be like y equals 5 plus 0.40 times x. Well, what we can do with the 0.40 represents our slope. Even though it's listed at the end, slope is always supposed to be multiplied in front of the x. And we can easily turn that into a fraction. 0.40 is the same thing as 4/10. I can actually write this as 4/10 times x. And that fraction 4/10 can then be simplified one more step to turn it into 2/6. So we can see that we have a y-intercept of 5 from the equation that we already talked about. We already have that point on the graph. But now, if we think about that slope of 2/6, that's rise over run. So from one point to the next, we're going up 2 spaces. Yep, we went up 2. And then we went over 5 spaces to get the next one. So that's kind of another cool way to think about getting some more points. So I'm just going to actually continue with using the slope. So from this point here, I'm going to go up 2 over 5, up 2 over 5, and just continue that pattern to get some more points here on the graph. All right, now actually, looking back at this, we're going to need to make an adjustment for the very last point. Because if you notice here, that's on top of 25 ounces. Can we buy 25 ounces? No. Most we can have is 24. So we actually need to go back a square to 24 ounces. And here we can just sort of estimate the price. I mean, it's pretty close to $15, but it's 40 cents less. So I'm going to actually make the last point here. 24 ounces is $14.60. So that's probably going to be more somewhere like this. And I can even put a little label to that point to kind of remember, like, that was the exact position of my stopping point. 24 ounces cost $14.60. All right. So we have our graph. I suppose we could also go ahead and connect this, but I'm going to make it stop at that final point. So rather than doing like an arrow to show that it continues on forever, like we've done for some other graphs in the past, this one has a clear stopping point. All right, so now the graph that we've made is going to allow us to identify the domain and range of this function. So what the domain is, I'd love for you to write this down. We've seen this word before, but let's just review. The domain is representing all possible inputs. When we're using x and y for the variables, x is the variable that we use for the inputs, and some math teachers might say the domain is all the possible x values, all the possible values for x. In our case, the input is the number of ounces. So our domain is going to be the possible number of ounces. So on your paper, I would like you to write down what is the domain. So it's essentially from this number to that number, what are all the possible ounces that you could have? All right, awesome job. So just putting a little context in here, yeah, you don't have to buy any ice cream, so it could be 0 ounces, but the most you can get is 24 ounces. Notice how domain is in line with, if we look at the x direction here, like horizontally on our graph, it's like the end points that correspond with the x-axis. All right, so that's our domain. Now let's talk about the range. Make a little line over here. The range is just the opposite. The range is describing all the possible outputs. So similarly on this one, I want you to fill in these blanks. What are all of the possible outputs here for our graph, from what number to what number? All right, awesome job. So because range is representing the cost, it's the dollars, the minimum amount of money that we would need to bring is $5. And the maximum we can spend, according to how they've limited how many ounces we can buy, we see is $14.60. And so the way that we find the range here on the graph is we're looking at the y-axis now, and we're looking at, okay, it's kind of like, what's like the lowest possible y value? Well, that's 5. The highest possible y value that we have over there is $14.60. All right, so that was doing some work and some analysis and looking at the graph of what we're calling our original function. So the original function is where we input ounces and we output dollars. Well, what we're going to look at now in part 2 is the inverse. So first off, this equation should look familiar. This is using the inverse notation here with a little -1. So that's how we know it's the inverse of our original function, f. And this one is based on the dollars. So this is now going the other direction. If we know how much money someone brought, we can plug that in here, subtract the $5 to get in the door, divide by 40 cents to see how many ounces we can buy. And so I do just want to make a little note here that this f inverse of z is really representing the variable z. So it is going to give us the ounces. All right, so we've sort of already answered together here part A and B. We know that when we're looking at the inverse, the input and the output variables switch places. And so dollars used to be the output of the original function. Now for the inverse, dollars have become the input, and now we have ounces for the output. We're going to do the same thing now. We're going to use that to help us label the axes on our graph. The input is always going to go on the x-axis. So for this inverse function, we saw, well, now the input is dollars. So we are going to put that on the x-axis. Now we have ounces for the output, so that is going to go on the y-axis. All right, let's do the same thing here with labeling our scale, so we can have each square represent 1 unit. And I'm just going to label here counting up by 5. All right. Now, I want to give you some ideas, some guidance in how we can think about graphing this function using some information that we've already seen from the other graph. So rather than looking at the equation on this one, let's actually go back and look at our first graph. And I know that we labeled one of these points with an ordered pair. We did that at the very end. I'm going to actually go back and label all of my points with ordered pairs, because what these are really just representing different pairs of, if you buy this many ounces, it's going to cost this many dollars. So what we have represented here, we already have these different combinations. We have like 6 combinations listed of ounces and dollars. Well, when we're graphing the inverse, it's still representing ounces and dollars. We just switched the axes. The input and the output switched, but it is still going to represent the same information. So for example, looking at the very first point, if you buy 0 ounces, it's going to cost you $5. Well, let's put that information on the new graph. If we buy 0 ounces, it costs us $5. That's interesting. That point used to be a y-intercept. Now on the inverse graph, it's an x-intercept. It just switched. Let's look at the next point. So the next point right here is if we buy 5 ounces, that costs us $7. So let's find where 5 ounces would be, and then $7 is going to be right there. So following that same process, I would like for you to go ahead and transfer the remaining 4 points using the information that we got from the first graph. On the second graph, the other thing that I'd like you to go ahead and fill in now, so we'll check the position of your points, but I would also like you to write the ordered pairs next to each one, still putting the input value first, so now dollars is listed first, and then ounces is listed second. All right, and then the other piece that it was asking us to do here in part C, once we've made the graph, is to now identify the domain and range of F inverse. Looking at this new graph, let's fill in the spaces for the new domain and the new range. So I want you to go ahead and try that part on your own. All right, so when we're thinking about domain, now domain is still what are all the possible inputs. Well, the inputs for the inverse here are dollars. So it's the minimum amount of dollars up to the maximum amount of dollars. Range is still what are the possible outputs. Well, now the output is ounces, and so it's 0 ounces to 24 ounces. So let's see if we notice anything. If we look back at the domain and range of the original function, would you tell your partner what is something that you noticed? Like, how did the domain and range compare for the original graph compared to the inverse graph? All right, so hopefully we're seeing here that they just switched. So the domain of the original graph, 0 to 24, that became the range of the inverse. The range of the original, 5 to 1460, that became the domain of the inverse. So noticing here the domain and range is the same information, it's just represented differently because the input and the output change. So if domain and range is based on the input and the output, it makes sense that that would also change, like they also just switch places. All right, so let's take a look then at the next question down below, number 3. What did we notice about the graphs of the two equations, and how are they related? And so to help us think about this, I wanted to actually be able to display and show our graphs side by side. And we saw that there was a special connection here with the ordered pairs. So in the original graph, we saw that the ordered pair, the first position was representing ounces, the second position was representing the cost in dollars. And then we saw that that just switched when we went to the second graph of the inverse. Now the first number was representing price in dollars, and the second number was representing the ounces. And so literally we're seeing like the X and Y position from each ordered pair just switched places. So let's make a note of that here. In question 3, one of the things that we notice here is it looks like, if we just think of these ordered pairs as being little X and Y values, we see that the X and Y values switched. And this is something that will actually always be true for the inverse graph compared to the graph of the original. Another thing that we saw, what was causing those X and Y values to switch, were the axis labels. So first one we have ounces on the x-axis, then we have ounces on the y-axis, the cost position switches. If the axes represent the location of the input and the output and output switch, so the labels are going to switch as well. So I'm going to make a note of that just because visually that was a big difference between how the graphs looked in terms of how they were labeled. So I'm going to say here the axis labels are switched. But in terms of how they are related, let's also make a note here that both graphs still represent the same information. It's just sort of the difference in like the order that it's presented. So if you wanted to know the cost for 15 ounces, you could find that answer from the original graph, or you could find it from the inverse graph. It's the same information, it's just a switched order. Now, there is one other thing I want you to know and be aware of about the graph of a function and its inverse. So there's another cool thing that happens. So I'm going to go back here to where we're seeing both graphs side by side. And I'm just going to think about, like, if I were to put some labels on here, we've got our original function, and then over here we have the inverse. So if we were to draw in a special line, I'm going to draw the line in first, and then we'll talk about the significance of it. So it's a line that starts at 0, 0, And it has a slope of +1, meaning it perfectly passes through each little square diagonally. I'm going to actually draw that same line on this one as well. The equation for that line that I just drawn, that has a slope of +1 and a y-intercept of 0, initially we could think of it as being 1x plus 0, but if we simplify it, it's really just y equals x. And there's something really special about that line. If I were to reflect the original graph over that line, that means, like if I were to fold my paper in half over this line, the part where the graph would touch on the opposite side exactly lines up with where the graph of the inverse is. So let me see if I can show you that. So if we look at the first one, I can't exactly like fold my projection here in half, but let's look at this little piece right here. I'm going to highlight that in yellow. And if I were to flip that over to the other side, I'm going to try to make it stand out a little. So I'm going to think about putting it in green. I'm not going to do this perfectly, probably. I'll try my best, but it's going to look something like where this green line is. Let me use my hand over here one more time. Yellow part is going to flip over the dotted line, and it's going to end up where the green line is. Can you sort of visualize that? If we can fold it. Let's look at the other part. If we were to take this part, let's maybe make this pink. And if we think about taking the pink part and like folding it over the red dotted line, it's going to be, see if I can do that a little bit better. It's going to be probably right about here. So that's what it would look like on the other side. Now, that big green line that I drew, this turns out that that is the exact same position of the inverse. So if you see that this line is really like the exact same as that one. And I won't do the whole drawing on the other one, but the same thing would happen if we were to take this green line over here, flip it over, it's going to be the pink and yellow line. So that is another characteristic that's always true for the graph of a function, an original function and its inverse. So I would love for us to add that to what we've written down here in number 3, and that is that the graph reflected over the line y equals x. All right. So let's take a look at the last question now at the bottom. So we have another student here named Ross, and he shows up for the event. He ended up spending $9.40, and so we want to figure out how much yogurt he could get. What I might think about on this one is just plugging that into our inverse formula. This one is super helpful if we know the amount of dollars that was spent. This is what's going to help us to work backwards and figure out how many ounces could be purchased. So let's just see what happens here if we plug in the 940 in place of D. So this division is going to work out actually really nicely. So 440 divided by 80 cents is going to give us an answer of 11 ounces. Now, if we try to take a look at where that point is on the graph, let's look at that actually on both graphs. So if we were to bring 940, that's going to get us 11 ounces. So 940 is going to be right about here. And I can see where that is touching the line here. That's giving me this value of 11. And I can tell from the graph that there's no other amount of yogurt that he could have got with that amount of money, because there's no other point that is going to touch the line. Even if I try to continue like going really far on forever in this direction, like it's never going to touch that line again. There's no other amount of ounces he could get. If we were to look at that on the graph of the inverse, bringing $9.40 would be right about here. Going up to the graph of our line, we can see this is about where it's going to hit. And going over, sure enough, that is giving us 11 ounces. And so we're seeing the same thing here on the second graph. Like, even if we were to draw our line upwards and onwards, we're not going to touch the line again. So there's no other possible amount that you could get. So let's just make a little note here. No other amount of yogurt would cost $9.40. And so what we're noticing here, because there is only one output for each input on the original graph, actually let's look at this one. The original graph, every input only has one output, so this is a function. But notice that on the inverse, each output also only has one input. And so the graph of the inverse is also a function, just like the graph of the original was a function. And so that's that word that we looked at the very start today. We're going to say that this is a function that is invertible. So let's add in here that the inverse of f of z is also a function. So that means that f of z is invertible. And I almost messed up that word at the start today. Invertible doesn't just mean that you can find the inverse. It means that when you do find the inverse is also a function. The definition for a function is that each input can only have one output, whatever you define your inputs and outputs to be. Another connection that we talked about earlier in the year, when you are looking at the graph to tell if something is a function, it has to pass the vertical line test. And so if we look back at these, both of these here, I feel like this one is, maybe I'll go back to the original one. Both of them pass the vertical line test. So the first one here, vertical line only crosses through one time. When you look at the inverse, a vertical line only crosses through one time. Now actually, we're going to talk about this in the quick notes when we finish up, but there's an even faster way to tell if something is invertible just by looking at the original graph. And that is a new test that we're going to call the horizontal line test. So it turns out that if the first one passes the vertical line test and also passes the horizontal line test, meaning a horizontal line only crosses in one place, that is actually enough to tell you that the inverse is also going to be a function. All right, so let's turn over to the other side here. So we're going to finish up here with our quick notes. This is where we're going to put in just some more detailed information, kind of summarizing. We talked about a lot of different things today, looking at the graphs of inverses. So the first and second learning targets were all about the graph and also what's happening with the domain and range. So I'm going to start this here on the left-hand side, and let's just call this graph of inverses. All right, so some things that we saw today. We saw that the graph of a function and its inverse and I'm going to put in a little notation there for inverse, the little f to the negative 1. The original function, we would just call that regular f. We can say here that these are reflections over y equals x. All right, we also saw that the domain of F was equal to the range of F inverse and the range of F equals the domain of F inverse. And this is all happening because the inputs and outputs switch. All right, and then this whole other side is about our last learning target, which is all about if a function is invertible. So let's start with this. On this side, we're going to say that a function is invertible, and let's underline that line, so that's what this whole side is about. Another name for being invertible is one-to-one. And that happens, it's invertible if its inverse is also a function. So generally the definition for a function is that for every input, I'm just going to use an x there, so like for every x value, there is exactly one y. That's what we're checking when we do the vertical line test. Every x value only has one y value. But in order for it to be one-to-one, when we switch the x's and y's, and we still have that result be a function, then another requirement must also be true, and that is that and for every y value, there is exactly one x. And that is what we can test with a horizontal line test. If you do a horizontal line, you're checking for a specific y value, how many x values it has. Well, if it only crosses in one place, then it only has one x value. So let's just make a little note here that you are just looking at the horizontal line test for the original function. I'm just going to write here that the original function, in order for it to be invertible, it must passes the horizontal line test. So a quick example here, if I had a graph that looked something like this, it kind of has all of these ups and downs and some curves, this one does not work. It is not invertible because it does not pass the horizontal line test. I'm seeing that that line is crossing through like 3 different times. It does pass the vertical line test. So the original function is a function. That's fine. But if I were to switch all the x's and y's, what will happen is that these 3 points here, when all those y values become x values, then we're going to have like 3 different x values that have the same 3 different, one x. When you switch it, it's not going to work. Think about switching it, it's not going to pass the vertical line test.